This is part 13 in a series of videos in which I'm developing this magnetic core memory system. In the videos in this series so far, I've gone through the basic development of this system. This series of videos is really to promote a book I'm about to release that details this and goes through the entire process and shows the schematics and the way I went about developing this. But in the videos I wanted to give a fairly brief overview of how the system works, the approach I took to developing it, and we've got as far as getting the first main prototype board fully functional. It's now working, and somebody asked me a few days ago how I went about testing this, because I have mentioned that the testing is fairly complex, and so I thought in this video I would go over the types of testing I do for this. And in fact, this technique is very useful for fault finding when you're repairing vintage equipment. And as I say, the technique is very useful for detecting and locating erratic or poor signals that you can get in digital systems. And that's really what I'm looking for in this system, is to make sure that I optimize the quality of the signals I'm getting out of the magnetic core detection system. So what I've got set up here is a small demo board running a PIC microcontroller, and this is running in a very similar way that something like a Z80 processor would, and I currently have the memory card, the memory board set up as if though it was an SRAM, so I no longer have the external pulse start pulse running, so I've got that disconnected, and it is now running in its automatic mode where it automatically detects when a read or write operation is required. By read or write, I'm talking about read or write from the perspective of the host system. With a magnetic core memory system, every cycle is in fact a read followed by a write, but all that is taken care of internally. As far as the external control and bus is concerned, what I have connected is a 6-bit address bus, 64 bytes, an 8-bit data bus, and a chip select line and a read-write line, and the 2 power lines. That's all that's connected. There is no start pulse. That's all taken care of automatically by the logic control on the memory card itself. But one of the complications in developing something like this that I'd mentioned previously was the variability in lots of different aspects of the operation of the system. So for example, if we take just one of these mats, so this is an 8-bit memory, and there is one of these mat arrays for each of those bits, and each of those mats contains 64 ferrite cores. So if we take just the first one as an example, then when we're trying to test this, every single core on that mat is handled by a single sense amplifier. So there's a single wire that runs through all 64 cores, and that means that any variability in the cores themselves has to be catered for by the sense amplifier. Now on top of that, all the X cores for each of the X lines go through 8 cores on each mat, and each of the Y wires goes through 8 cores on the same mat. So in other words, there's a lot of interaction between the various wires. Now on top of that, if we look at the X and Y drivers, then they are of course current limited, so they are giving very specific currents on the wires. But when you think about it, that means that if you take the 8X drivers for example, they are going to vary slightly in the current that they are applying to the wires, and the same with the Y drivers, they will be applying slightly different currents, on top of which it's a highly inductive system, so that's going to have some impact as well. And that means if for example we take the X0 and Y0 drivers and turn them both on, then the combined current is not necessarily going to be the same as the X0 Y1 combination. That means that we already have 256 combinations just for the combined currents for the select drivers, We then have another 8 drivers for the inhibit, and again they will introduce variability as well. And on top of that we have the issue of there is a lot of cross-coupling between the various wires, and the effect that will have will vary depending on the actual bit pattern that's been applied. We then have an even bigger complication that all the X wires go through every single mat. So all the X0 wires, or rather the X0 wire goes through all the X0 cores. So every single selection wire actually goes through 64 cores. And the interaction you will get depends on the bit pattern that is being applied to each of the mats. That in turn is cross-coupled to the inhibit wires and the sense wires, so there's a huge amount of interaction that we get. So we have variability because of the cores, we have variability because of the differences in the tolerances for the current drivers, both for the selection and the inhibit drivers. We have variability in the sense amplifiers themselves. We've got drift with temperature, external influences, variability in power supply, and when we put all those together we have an almost infinite number of possible permutations. So the initial testing I was doing was using something like this, which allowed me to manually set addresses and data bit values. But of course that's not much use when we want to do a very in-depth test, because we need to carry out hundreds of thousands of permutations in testing. Just the variability on a single mat caused by the X and Y driver combinations and the ferrite core combinations themselves requires 130,000 individual tests, and so it's not feasible to do all that by hand. And then when you introduce the other variabilities, then it just becomes completely impractical. So the way I go about testing this is I have the demonstration board that is going through and repeatedly writing every single combination of values to the memory. So each of the 64 bytes is written with a certain value. They're then all read back. The PIC then moves on to the next value, reads it all back. It then skews the values, so it will write a 0 to the first memory location, a 1 to the second, etc. So it goes through a whole range of, or the entire range of possible combinations, and then it reads them back as it's doing that to make sure that the memory is properly responding and storing the data. Now, if it detects a fault, then the error count that is maintained by the demonstration board is incremented, and the 3 LEDs at the bottom of the screen here on the right are showing the incremental error count. So it's a binary representation of the current error count. It should stay off if we're not getting any errors, and then the second LED from the left is just to show us that it's actually running. So when I start this up, we should see all the 3 LEDs on the right stay off, and just the second one from the left should be illuminated. So I'll power this up now. It takes about 2 or 3 seconds to do a reset, and so it is now running. You just saw the LED dim very slightly, that means it's started running. And also we've got something appearing on the scope. Now what I've got the scope set up to do is the green trace is the start pulse that's generated automatically by the system when it detects a requirement to read or write the memory. The yellow trace is the read-write line, and the blue trace is this probe, which currently isn't connected to anything. I'll use that in a few minutes. The way I've got the trigger set up on this scope is it's set up for a pattern, and it's looking for a logic high on the read-write line, in other words read mode, and it's looking for a high on the start pulse. So in other words, it's going to show us or capture every single read event when the system's running. So if I take this probe and we look at the output from the bit 0 amplifier, so that's this top left hand mat, and then we do a single capture, then what we have here is the yellow trace is high, showing as we're in read mode. We've got the green pulse, that's the start pulse, and then if you recall from the previous video, this falling edge of the green pulse is the sample point for the system. So if the signal from the sense amplifier, which is the blue trace, is low at this point, that's a 0. If it's high, it's a 1. And because this is going through a whole range of values, if we keep doing single captures, then we'll see that we randomly will detect either a 0 or a 1. So this is of course a 1. If we do a few more, that's a 0, a 1, another 1, a 0, 0, 0, 1. So you can see we're capturing single events, but to go through this and try and manually capture every single permutation would be pretty much impossible. But what we can do, of course, is just put this into auto, and this is now going through and showing us every single capture. And so what we have on the left is the variability showing up now of the 0 values that are being read, and on the right here we can see the variability of the 1 values. And this is what I'm talking about. You can see there's quite a large variability caused by the variations in all the things that I mentioned, whether it be down to the XY driver current, inhibit current, sense amplifier variabilities, or just the core itself. You can see that we're getting quite a lot of variability. But the point here is that the falling edge of the sample pulse, the green pulse, is fairly well into the center of the switchover band, which is what we're aiming for. We need to make sure that we're not getting too close to this area here, where we're getting into the grey area, or too far this way. If we adjust the sense amplifier threshold, this entire thing will move up or down. So if I try to adjust the threshold of the sense amplifier, you can see that as I turn it one way, then the window starts to move in one direction, and if I turn it the other way, it starts going in the other direction. Incidentally, I've got, if we look at the display setting on here, I've got persistence set to 5 seconds on this display, which is why we're seeing this persistent view rather than just a single trace each time. Okay, so as you can see, I can adjust the threshold fairly accurately to center this, and that allows me to center and cater for all the variability in the system, and I can do that for each of the 8 channels. The falling edge position for this green trace can also be adjusted, so that is this pot at the bottom right, and that just sets this pulse width. The rising edge of this is the point at which the system detects a requirement for a read or write, or if we're driving it with an external pulse, it's the rising edge of the external pulse. And the falling edge is a timed event that we can adjust. So in other words, we can set the operational characteristics of the system fairly accurately. And one of the things we have to be able to cater for is variations in temperature, but also power supply. I'm driving this from the bench supply at the moment, and although the supply would normally be fed from a regulated supply, it's still going to vary a bit, especially when we consider that the difference between the system peak current when it's writing all ones to the system compared to when it's writing all zeros to the system. When it's writing all ones, the peak current drawn is about 600 milliamps, and when it's writing all zeros, the peak current is about 4 amps. Although a very short duration current, so the average current is much lower than that. At the moment it's reading and writing about every 5 microseconds, so it's running quite quickly at the moment. But even so, with this spread of values that we are reading and writing, the average current drawn by the system at the moment is about 350 milliamps. So it's quite low. but because of the peak currents that the system is seeing, that will cause variability as well. And so we need to make sure that the system is capable of dealing with that. So if I now adjust the voltage that we're feeding to the power supply of this board, I'll change it by 5%, I'll lower it by 5%. You can see that causes a lot of problems, and it's now introduced a lot of failures in the system self-test. So what we'll do now is adjust the threshold of the amplifier for that bit. Just taking it down very slightly, and so you can see now that we are back within the correct range. I'll reset the board, clear the sweeps, wait till it starts up, and so as you can see, just clear that again so it's a bit clearer. So as you can see, it's now working fine and we're not getting any errors. The reason we're getting errors on this channel is because I, as you saw, adjusted the channel and it was incorrect. If we now go back to the voltage that we had previously, okay, you can see that even though the voltage has now changed by 5%, it's gone up by 5%, this is still working fine, and also we're not getting any errors showing in the system. If we go to the next bit, that was bit 0, if we go to the next bit, you can see that's giving very similar results. And the next, okay, so we can do that with all 8 bits. And using this technique, it gives us a very good insight into exactly how the system's behaving, whether or not it's correctly adjusted, and moreover, it shows us the entire spread for the operation of the entire system, and it would be very difficult to do this manually. And that's how I've gone about testing this system. So as I've developed this, I've done a lot of this sort of testing, and that's how I have optimized the system to make sure that it behaves itself. And it's got to the point now where I left it running for 12 hours, running at this rate, and it didn't come back with a single read or write error. So it's looking extremely robust. This is a final test. I'll show you what happens when we introduce an external influence. So I showed you previously that if you put a magnet near this when it's running, then it causes the system to fail, which you would expect it as a magnetic system. So I've got our magnet again, and if we watch the trace as I bring this closer to the system, so as I start lowering it, you'll see that the window is starting to move and close up. It's getting very close now. If I take it away and wait for the persistence to die away, you see it's back to where it was. But if I go even closer, you'll see at some point the values will go beyond the falling edge of the green trace, and when it does that, as you can see, we get an error showing up. If I put it even closer, we'll get a lot of errors. So as I said, very good way of testing this, and it does mean that the system can be developed and made very reliable. And this technique actually works extremely well if you're repairing old vintage computer equipment and you're having intermittent faults. Then looking at certain signal lines using a technique like this will really show up any failing parts, even if they appear to be working for the most part. This is a very good way of looking at the quality of signals over time, rather than just instantaneous values which may not show anything. Okay, so that's how I've gone about testing this. This is now complete, the design's finished, so I'm just going to finish off the book, make it available, and then I'll make these boards available as a kit. There will be bare boards, and what will be in the kit will be the main logic board, the array board, the cover, the plastic nuts and bolts that are required, suitable wire, and a set of ferrite cores. along with instructions, etc., as to how to assemble it, although most of the information for this will be in the book itself. Okay, if you've got any questions or you want to see any particular testing with this, then please leave a comment.